Okay, let's look at this integral transform called the Laplace transform. It is an integral transform. It takes a function in one space. In this case, we usually consider our functions to be in the t or time domain, we might say, and it transforms it into another space. So our outputs will be in what we call the s domain. The most famous of all the transforms, of course, is the Fourier transform, which is a little different. It's kind of similar to the Laplace transform, but it's different. So it is this integral. We take our function, f of t, and we take the integral from 0 to infinity, e to the negative st dt times that under the integral. And here's the idea. This is where we'll be using the Laplace transform. We have some differential equations, some dE. We could just do the hard calculus, solve the differential equation, and get our solution. What the Laplace transform allows us to do, though, is we take the transform and we end up in this different region. Instead of having our variable t, our variable will be s. Over here in the s domain, instead of doing hard calculus, we do relatively simple algebra, solve whatever we get for what we'll call capital Y of s, and then we undo our transform, do the inverse Laplace transform, and we get our solution to the dE. So we're going to go around this circle rather than just doing calculus and getting our solution. For most of the problems we will do in a standard dE class, a lot of times it would be easier just to do the calculus. But sometimes in the real world, it's easier to go around this way than to come straight across. Okay, let's do some Laplace transforms. We're not solving any dE's yet. We're literally using the definition of the Laplace transform right here to find the Laplace transform of 1, y equals 1. By definition, that's the integral from 0 to infinity, e to the negative st times 1 dt. Okay, we're going to do this formally. Once we do several of these, we'll get a little hand wavy with that infinite limit, that limit of integration right there of infinity, because we know how to handle those by the time we get to dE, but I am going to write this one up formally. So technically, when we have an infinity as our upper limit, we're supposed to put a b there and say the limit is b goes to infinity. And then we'll do this antiderivative, do this definite integral, then we'll take the limit as b goes to infinity. So of course, the antiderivative of e to the negative st is negative 1 over s e to the negative st evaluated from t to b. So I've just plugged in my limits here, top minus bottom. Now we take the limit as b goes to infinity. This term here will go to 0. Remember, these are t's we're plugging in. You got to be careful when you're doing Laplace transforms by the definition, because you have two different variables inside your integral here. We're integrating with respect to t. That's my variable. That's what I'm plugging in. Our answer is going to have s's in it. So I plugged in t equals 0 and t equals b. When b goes to infinity, this term goes to 0. So we get 0 minus 1. Those negatives cancel and we get 1 over s. So this is counterintuitive. You would not expect something like this. But the Laplace transform of just the number 1 is 1 over s. Okay, so if you're doing Laplace transforms, the next thing you might think to try would be, say, x. Well, remember, we're not using x as our independent variable here. We're using t. So we might try the Laplace transform of t. Okay, by definition, that's the integral from 0 to infinity. We always have this e to the negative st there and the dt, and we just take our function and stick him right there. Okay, again, I'm going to be formal here and say, well, this limit of integration of infinity, we put a b there, and then at the end we'll take the limit as b goes to infinity. You might remember that from Calc 1. So let's find the antiderivative of this. We'll do the indefinite integral first, and then we'll come back and do the definite integral. We have to do integration by parts here. So I'll let u be just t, du is dt, dv is whatever is left over, and then integrate that to get v. And then here's our formula for integration by parts. So here is the antiderivative of that function, the indefinite integral. Now we can plug in our limits. Our limits of integration here, 0 to b. So just evaluating this whole thing from 0 to b. Then I'll take the limit as b goes to infinity. And you can check all these details here yourself, and you should. But remember, I'm plugging in t equals, not s equals. By the time you're done, all your t's should disappear. When you're doing a Laplace transform, if you have any t's left over at the end, you have done goofed. You're integrating out the t's. It's your variable of integration. Okay, once we get to here, we've plugged in our limits, t equals 0 and t equals b. This term here, b is going to infinity, so the negative b wants to go to negative infinity. E to the negative infinity, that wants to go to 0. That's an infinite limit, and it's one of those ones where you have to figure out, you have to use L'Hopital's, because we have two different kinds of behavior. One goes to 0, one goes to infinity. 0 times infinity. We have to see who wins. Exponentials beat any polynomial. This exponential goes to 0 faster than b goes to infinity. So this term goes to 0. Similarly, this term will go to 0. E to the 0 is 1, so we get a minus and a minus. This is just 0. We get 1 over s squared. So the Laplace transform of t is 1 over s squared.